Today we're diving into a paper that explores a new way to improve the performance of large language models, LLMs. The paper, Large Language Monkeys, Scaling Inference Compute with Repeated Sampling, investigates the impact of increasing the number of samples generated during inference. What's the main idea behind this approach?
The paper argues that we can significantly improve LLM performance by increasing the amount of compute used during inference, not just during training. Instead of relying on a single attempt to solve a problem, they propose generating multiple samples and then using a verifier to select the best solution.
So instead of just relying on a single guess, we're essentially giving the model multiple chances to get it right.
That's interesting. Can you explain how this repeated sampling approach is implemented?
The process is fairly straightforward. First, the LLM generates multiple candidate solutions for a given problem. This is done by sampling from the model's probability distribution, often with a positive temperature to encourage diversity in the generated outputs. Then, a domain-specific verifier is used to evaluate the generated samples and select the best one.
And what kind of verifiers are we talking about here?
The type of verifier depends on the task. For tasks like coding or formal proofs, where solutions can be automatically checked, the verifier might be a unit test suite or a proof checker. For tasks like math word problems, where automatic verification is more challenging, the verifier might rely on techniques like majority voting or reward models. So the paper focuses on two key aspects of this repeated sampling approach: coverage and precision. Can you elaborate on these?
Yes. Coverage refers to the fraction of problems that can be solved by at least one of the generated samples. Precision, on the other hand, refers to the ability to identify the correct sample from the collection of generated outputs.
It seems like coverage would be directly related to the number of samples generated. The more samples you generate, the higher the chance of getting a correct solution. Is that accurate?
That's generally true. The paper shows that coverage consistently increases as the number of samples increases across a range of tasks and models. They observed that the relationship between coverage and the number of samples often follows an approximate power law, suggesting the existence of inference timescaling laws.
That's fascinating. So we're seeing a predictable relationship between the amount of compute used during inference and the performance of the model. But what about precision? How does that factor into the overall performance?
Precision is crucial, especially in domains where automatic verification isn't readily available. The paper finds that common verification methods like majority voting and reward model scoring plateau beyond a certain number of samples. This means that even though coverage continues to increase, the ability to identify the correct sample doesn't necessarily scale with the sample budget.
So there's a potential bottleneck in the verification process. Even if we generate a lot of samples, we might not be able to effectively identify the correct one. What are some of the challenges associated with verification?
One challenge is that the correct solution might be a rare occurrence among the generated samples. For example, the paper shows that for some math word problems, the correct answer is only generated in a small percentage of the samples. This makes it difficult for verification methods to reliably identify the correct solution.
That makes sense. So how can we improve the precision of these verification methods?
The paper suggests that developing more robust verification methods is a key area for future research. One approach might be to leverage the reasoning steps generated by the model, not just the final answer. This could provide additional information that helps the verifier distinguish between correct and incorrect solutions.
That's a promising direction. Let's shift gears a bit. The paper also explores the cost implications of repeated sampling. What are the trade-offs involved?
Repeated sampling can be more computationally expensive than using a single attempt. However, the paper shows that in some cases, it can be more cost-effective to use a smaller, cheaper model with many samples than a larger, more expensive model with fewer samples. This is because the performance gains from repeated sampling can outweigh the increased cost of generating multiple samples.
So there's a potential for cost optimization by balancing model size and the number of samples. That's interesting. What are some of the limitations of this repeated sampling approach?
One limitation is that it can be computationally expensive, especially for tasks that require a large number of samples. Another limitation is that it relies on the availability of effective verification methods. If we can't reliably identify the correct sample, then the benefits of repeated sampling are limited.
So there's still work to be done in terms of developing more robust verification methods. What are some of the potential future directions for this research?
The paper suggests several promising avenues for future research. One is to explore more sophisticated sampling techniques that can generate more diverse and informative samples. Another is to investigate the use of multi-turn interactions, where the model can iteratively refine its solutions based on feedback from the verifier. Finally, it's important to consider how to integrate repeated sampling into existing LLM inference systems and optimize for efficiency and cost.
So there's a lot of potential for further development in this area. To wrap up, can you summarize the key contributions of this paper?
The paper demonstrates that scaling inference compute through repeated sampling can significantly improve LLM performance across a range of tasks and models. They show that coverage often scales log linearly with the number of samples, suggesting the existence of inference timescaling laws. However, they also highlight the importance of developing robust verification methods, especially in domains without automatic verifiers.
This was a great discussion on the technical aspects of this paper. Thank you for your insights.